All right, so I want to pick up right where we left off last night, which is we're talking about hypothesis testing, and we went through basically the logic of the procedure, how it works. Now, I do want to point out that there are two different methods for hypothesis testing, and we're going to look at both of them. In our book's terminology, the first one is called the classical approach, and the second one is called the p-value method. I'll get to that one later. So for now, we're talking about the classical approach, okay? So for the classical approach, we need to find something called the critical value. The critical value is the z-score beyond which we will reject the null hypothesis. If our test statistic lies beyond that critical value. And remember, we already talked about the test statistic last night. That is the z-score that you calculate based on your sample data. So the critical value is the z-score that separates what is called the rejection region. Let me just write that out to make sure I'm being clear. Okay, the rejection region from the non-rejection region. Okay? And your critical value depends on two things. The first thing is the significance level of the test. Okay, remember that that significance level is equal to alpha, and the type of the test that it is. There are three types of tests. We went over these last night: two-tailed, left-tailed, or right-tailed. Exactly the three that are shown right here. All right, so those are the two things that the critical value depends on. All right, I'm going to erase and scooch down a little. All right, so these are basically our three cases: two-tailed test, left-tailed test, right-tailed test. And remember, what kind of a test it is depends completely on the alternative hypothesis. In the two-tailed test, that's H1, your alternative hypothesis is that your proportion is not equal to the hypothesized proportion, which is given in the null hypothesis. For a left-tailed test, your null hypothesis is that your proportion is less than the hypothesized proportion. And for the right-tailed test, your null hypothesis is that the proportion is greater than the hypothesized proportion. Okay? So for all three cases, the hypothesized value, the one that is in your null hypothesis, and remember, your null hypothesis for a proportion test is always going to be that p equals a certain value, p0. That's supposed to say p0, okay? And that hypothesized value is always at the center of the normal curve. So it is, for all of these, p0 and here is at the center. When we standard normalize it, therefore it corresponds to a z-score of 0. So that is why, these curves are labeled with 0 right in the middle. Okay? So what we are looking for is we want to see if our sample data is close in here to the center, or is it way out in the tails, far away from the hypothesized value. Okay? And again, the type of test depends entirely on what the alternative hypothesis is, your H1. That is very important to correctly write H1 because that will determine if it's a two-tailed test, a left-tailed test, and a right-tailed test. It will also then determine where your do not reject region is and where your rejection region is. So for example, for a two-tailed test, you have these two critical values, beyond which you would say, well, that sample data is really far away from my hypothesized value, so therefore I'm going to reject the null hypothesis. Same thing for the left-tailed or the right-tailed test, but in that case, there's only one rejection region, either on the left or on the right. Okay. All right, I'm going to erase and go on to the next page. So how do we find these critical values that separate the rejection regions from the do not reject regions? Okay. Well, again, you have to have specified your significance level. So for example, let's look at a significance level of 5%. So in other words, we are saying that the significance alpha is equal to 0.05. All right. So for a two-tailed test, that means, okay, I want to take that 5% area, the significance, and put it into the tails. So this is kind of the opposite of the confidence intervals. When we did the confidence intervals, we said 95% confidence means we want to put 95% of the area in the middle, right? So now we are literally just turning that around the opposite way and saying, okay, well, we want a significance level of 5%, which means 5% in the tails. Okay. So 5% in the tails means we have 95% area left over. All right, and so for a two-tailed test, that means then, so there's 95% area in the middle, and as before, then we take the 5%, and because there is a tail on either side, then we want to divide that in half, and we get, 2.5% or 0.025 goes into each tail. All right, so there's 0.025 in the left tail, and there's 0.025 in the right tail. So this situation right here corresponds exactly to doing a confidence interval at 95%. So you should already recall what this critical number is. If you go to the table and look up the z-score that has 0.025 area to its left, you should remember that that corresponds to negative 1.96. Okay? And therefore, this value is its positive partner because it's always perfectly symmetric. So it's positive 1.96. Okay? So in this case, these are both the critical values. Okay? So in this case, we would say plus or minus z sub alpha divided by 2 is equal to plus or minus 1.96. Those are both the critical values for a two-tailed test at a significance level of 5%. All right, now here's where it gets a little bit different for the hypotheses tests compared to the confidence intervals. If we are just doing a one-tailed test, either left or right, then that means that all of the area of the significance goes into one tail. So again, doing this at a significance of 0.05, so alpha equals 0.05, in this case means we are putting all of that area, 0.05, into the left tail. So all of the 0.95 then is the rest of it. Okay. So now we specifically just want this z-score that has an area of 0.05 to its left. So if you go back to the normal distribution table and try to find that z-score that has an area of 0.05 to its left, this is a problem we did earlier, I think back in chapter 7, where it is exactly in between two z-scores. Okay, you should find that the area is exactly in between negative 1.64 and negative 1.65. Okay, so in that case, when the area is exactly in the middle, you just take the mean of the two numbers, which is then negative 1.645. Okay. So in this case, that is the critical value. It is actually equal to negative 1.645. And then if we move down to the right-tailed test, well, this is almost exactly the same case, except this time the 5% area is on the right. And we want the z-score that has 0.95 area to its left. And of course, it's just going to be the positive symmetric partner of this one. Okay, so in this case, the critical value is going to be positive 1.645. All right, I'm going to erase this and move on to the next page. Oops. All right, so here is just a summary of some important critical values. These values assume an area of alpha to the right of the z-score. Okay. So, for example, the one for the left-tailed and the right-tailed that we just looked up, that was this one. Okay. The z-score with 5% area to its right is 1.645. Or for the first case we looked at on the previous page, with 5% divided between two tails. Okay, so a z-score of 1.96 has an area of 0.025 to its right. Okay, so this table basically gives any of the critical values you might need. The only thing that you need to do is realize what type of a test it is. Is it two-tailed? Is it left-tailed? Or if it's right-tailed? If it is a left-tailed test, then you have to know to assign the negative sign in front of the number. If it's a left-tailed test, you know, like we just looked at 5% significance, then the critical value is not 1.645, it's negative 1.645. So you can certainly refer to these numbers, but you have to know whether it should be positive or negative. All right, I'm going to pause for a minute and then scooch to the next page. All right, so just before we actually work through a problem, let's just look at the methodology, and this is all straight out of the book. So again, what we're doing is we're testing a hypothesis regarding a population proportion P, and these are the requirements to use the methodology. You have to have a simple random sample or from a randomized experiment. And again, what that is, in your assignment, that's exactly what you're doing. You're randomly sampling from the data set in Excel. And again, you have to do this to make sure that the sample size is big enough. And third, the sampled values have to be independent. And again, in your assignment, that is the case because Excel samples with replacement. Therefore, each sample is independent. All right, you have to start by writing your null and alternative hypotheses. And again, the null hypothesis is always just P equals a value. P equals a value, P equals a value. That's it. It will always, always be an equals sign. For the alternative, there are three options. It is either a not equals, which gives you a two-tailed test. It is a less than, which gives you a left-tailed test. Or it is a greater than, which gives you a right-tailed test. You have to have a level of significance, alpha. And typically in the problems, that will be given. If for some reason it is not given, then just assume a very typical value of 0.05. Okay. All right, and what we are currently talking about, like I said, there are two approaches. We are currently working on the classical approach. So the first step is then calculate your test statistic z sub 0. And again, that is based on your sample data. P hat is your sample proportion. P0 is the hypothesized value. That is the number that is in your null hypothesis. And of course, as always, n is your sample size. All right, so once you calculate that, and then again, based on your significance level and what type of a test it is, then you look up your critical values, which then tell you where your critical or rejection regions are, and you compare your critical value with the test statistic. Or actually, I would think of it the opposite way. Compare your test statistic with the critical value. So, for example, if you were doing a two-tailed test, and if your test statistic z sub 0 is here, then you do not reject your null hypothesis, because that is not in the critical or rejection region. It's right here in the middle, close to your hypothesized value. Versus, let's say you're running a right-tailed test, and let's say that your test statistic z sub 0 is way out here in the tail beyond your critical value. So now it is in your critical or rejection region. So in that case, you would reject your null hypothesis. Because again, your hypothesized value is right here at the middle. And in this case, your sample data, well, it's way out here, far away. And so then you would say, well, this value can't be correct because my sample data is saying something else. I reject this number. All right? So that's basically, what this is saying. If your test statistic is beyond, outside the critical value, in the critical region, then in all cases, you would reject the null hypothesis. Okay. And then your final step down here, step 5, state the conclusion. And we'll go back to that when we do an example. But we went over that last night, and I kind of gave you the wording as far as how to state the conclusion, and that was on page 9. All right, I'm going to erase and move on to the next page. Okay, good. So yeah, let's start working on an example. All right, so here's the problem. 2011 National Institute on Alcohol Abuse and Alcoholism survey. 33% of American adults said that they had never consumed alcohol. In a more current random sample of this many adult Americans, 805 of them said that they had never consumed alcohol. At the 5% significance level, do the data provide sufficient evidence that the current percentage of American adults who have never consumed alcohol has changed from the previous value? Crap, hold on. All right, sorry, wrong number. Okay, so let's go back through the problem statement and write down, or just note all the important numbers. All right, so this 33%, this represents P0. Okay, that was the older, the known, the current status, 33%. All right, so we would, in decimal form, we would call that 0.33. So that's kind of our starting position going in. 33% have never consumed alcohol. All right, but then there was a newer sample. All right, so this right here is giving us the sample size, that's N, okay? And out of that many, 805 of them had never consumed alcohol. All right, so that's the number of successes, okay? So in other words, from that, we can calculate our sample proportion. So in other words, our p hat is, well, there was 805 out of 2,300. All right, and if you calculate that sample proportion, it is what? 0.35. So I think that actually divides out exactly. At the 5% significance level, all right, so that is telling us alpha is 0.05. Do the data provide sufficient evidence that the current percentage has changed? Has changed from. Okay, so those are kind of the key words right there. Has it changed from? It's not saying, is it less than or is it more than? Just has it changed? Or is it different? In other words, is it no longer equal? Okay, so you really have to read the words carefully and interpret, because that will tell us then how to write our alternative hypothesis. All right, so the first step always just writing the hypotheses. And again, the null hypothesis is always going to be an equal sign. So is the proportion equal to the value it used to be, which was 0.33, or the alternative is, based on this new sample data, has it changed? Is it not equal to that number anymore? All right, and again, writing that alternative hypothesis correctly is so important, because the entire rest of the analysis keys off of the symbol that you have used in H1. All right, step 2, significance level alpha. We already discovered that up here, that alpha equals 0.05. Step 3, compute the value of the test statistic. Okay, and remember that is your z sub 0, which is based on your sample data. And again, the formula for that, which we went over in class, is p hat minus p0 divided by the square root of p0 times 1 minus p0 divided by n. All of that under the radical. All right, we already know all those numbers, so let's go ahead and plug them in. Our p hat was 0.35 minus our hypothesized value, the value that we go into assuming is still true, is 0.33. All right, and then divided by square root of, okay, p0, again, 0.33. A 1 minus 0.33 is 0.67. And then divided by the sample size, which we know from up here was 2,300. And again, I think I mentioned this in class the other night, is, you're definitely going to want to put parens around this, and then probably an extra set of parens underneath your radical. Okay, it's very important to make sure you can do this correctly on your calculator. You should get 2.04. All right, so go through that computation on your calculator. Make sure that you can do that correctly. All right, I'm going to erase and scooch to the next page. All right, so on to the next page. And I just went ahead and recopied the null and alternative hypotheses up here so we could refer to them. So again, we are dealing with the classical approach. So we need to determine the critical value or values, and the first thing to do that is to determine what kind of a test it is. And again, determining what type of a test it is keys completely off the symbol in the alternative hypothesis, which in this case, because it is a not equals, means that it is a two-tailed test. Okay, two-tailed, meaning that, we're not sure in advance of getting the sample data if the sample is going to be higher or lower. It could go either way. We don't know. All right, so it's basically a two-tailed test, which means, again, here's our hypothesized value right in the middle, our p sub 0, which for our case is 0.33. We're going to have two critical values. Knowing that alpha is 0.05, again, that means that the rest of the area, the 0.95, is in the middle. We take that alpha of 0.05, we divide it in half, so either tail, both tails, have 0.025 area in them. And this is exactly the case that we had already looked up a couple pages ago. So we already know that this critical value is negative 1.96, and this critical value is positive 1.96. All right. And then what we want to do is compare where our test statistic falls relative to the critical values. All right, well, we just calculated our critical value on the previous page. It was our test statistic was 2.04. We just calculated that. Okay, so if we go ahead and add that to our figure, well, 2.04 is just a tiny scooch to the right of this. So it's somewhere up here. Okay, so that is 2.04. It is beyond the critical value. So in other words, it does fall in the critical region. Okay, it's past here. So in other words, yes, we are going to reject the null hypothesis. All right, that is going to be our conclusion, that we reject. All right. And again, you know, we went into this saying, well, the previous value was 0.33. That's right here in the middle, 0.33. We got this sample data, and our sample proportion of people who had never consumed alcohol was 0.35. And yeah, I mean, just intuitively, we know that 0.35 is greater than 0.33, but that's not enough to tell us whether or not we can reject that null hypothesis. Like, how much bigger is it, statistically speaking? So that's what we find out by calculating the test statistic and then comparing it to the critical value. It is, in fact, statistically significant. It is big enough that we can go ahead and reject our null hypothesis. And even though it's not that much bigger, it was based on a very large sample size of 2,300. So that helps add, you know, to the fact that, yeah, we are going to be beyond the critical value. All right, so we've done the test, we've rejected the null hypothesis. Now we want to state our conclusion. And again, you can refer back to page 9 in the notes where we went over this for the specific wording on how to do this. But in this case, we would say there is sufficient evidence at the 0.05 level of significance to conclude that the current percentage of American adults who have never consumed alcohol. And then what we want to put in here is basically the wording that goes along with our alternative hypothesis. So in this case, I'm just going to say it. It's going to take me too long to try to write. The current percentage of American adults who have never consumed alcohol is different from the previous value. Is different from, because that's what we said in our alternative hypothesis. Is it different from 33%? So yeah, in this case, we have concluded that there is enough evidence based on the sample to show that the current percentage is different from the previous value of 33%. All right, so again, that whole method that we just did is called the classical approach to hypothesis testing, okay, which involves taking the significance level, finding the critical values, which then identify the rejection regions versus the do not reject regions. Okay, so that is one way to do it. Now there is another way to do it, which is equivalent. It will give you the same answer. It's just a different method. So that's what we're going to do now, starting on the next page. It's called the p-value method. All right, so I'm going to erase everything and scooch on to the next page. All right, so on to the p-value approach. And again, we are doing the same thing here. We are doing a hypothesis test about a population proportion. The only difference is how we are going to make our decision about whether we reject the null hypothesis or not. Many of the other steps are exactly the same. So again, with the classical approach, which we just covered, you find the critical value or values based on your significance level. If your test statistic is more extreme than that, in other words, if it is outside of that, further away from the center, then you reject the null hypothesis. In the p-value approach, you still calculate the test statistic exactly the same way from the sample data. From that test statistic, you will then calculate this thing called the p-value. If your p-value is less than the significance level of the test, then you will reject the null hypothesis. And again, your significance level is your alpha. Okay, so if your p-value is less than alpha, then you will reject the null hypothesis. So again, p-value method. Instead of finding the critical value and region, we no longer need that. We find this thing called the p-value. And it really gives us more information. With the critical value and critical region method, the classical approach, it's basically either you reject or you don't. Okay? The p-value gives us a little more information about the result of the test. It essentially gives us a measure of the strength. Geez, how do you spell that? GTH. Okay. It gives us a measure of the strength of the evidence against the null hypothesis. In other words, are we really rejecting it by a lot, or are we just rejecting it by a hair, or what? Okay, it gives us more information. The p-value, it's just a probability. Okay, so it is a number between 0 and 1. Okay, so in other words, 0 is less than the p-value, which is less than 1. Okay. It represents how likely we would be to have gotten that particular sample data, or one more extreme, further away from the center, if the null hypothesis were true. Because again, you always go into a hypothesis test assuming that the null hypothesis is true. If you get a p-value that is very close to 0, it means that it is highly unlikely. Highly unlikely. Okay? And that basically just goes back to the scale of probabilities, that we learned back in chapter 5 from 0 to 1. Remember, 0 is impossible, 1 is certain, you got 50-50 in the middle. Anything close to 0 is a highly unlikely event. Okay? So if our p-value is down here close to 0, then it is highly unlikely that the null hypothesis is true. Okay? So in other words, if your p-value is small, in other words, if it is close to 0, and specifically If it is less than alpha, then you reject the null hypothesis. Okay? Because if you are down here with a p-value close to 0, then H0 is probably not true. It's probably not true because the probability of it being true based on your sample data is very small. It's very unlikely. All right. And then just a phrase, and this is from our old Triola book that we don't use anymore, but it's very helpful to me to help remember this, is that if the p-value is low, in other words, small, specifically less than alpha, okay, then the null must go. If the p-value is low, the null must go. In other words, we must reject the null hypothesis. All right, I'm going to erase and go on to the next page. Okay, so specifically finding the p-value for a one proportion z-test. So again, first we have to determine the type of test, which again keys completely off what your alternative hypothesis is. So it's either going to be a two-tailed, a left-tailed, or a right-tailed test. Second, you have to calculate your test statistic. And again, that is exactly the same. I'm just going to write it off here so I have a little more room. Your test statistic is calculated exactly the same way. Okay, your sample proportion minus your hypothesized proportion divided by the square root of p0 times 1 minus p0 right, divided by the sample size. So nothing new there. That's just your test statistic based on your sample data. And then third, okay, we have to actually find the p-value. The probability of getting that sample or one more extreme. Again, meaning even further away from the center, from the hypothesized value. All right, so for a one-tailed test, if it's either left-tailed or right-tailed, it's very straightforward. The p-value is simply equal to the area under the standard normal curve beyond your test statistic. In other words, further away from the center. Okay? So if it were a left-tailed test, and if your test statistic was here, then your p-value is just the area to the left of that. So you just go to the table, you look up your z-score, the area to the left, that's your p-value. If it's a right-tailed test, and if here is your test statistic, then the p-value is the area to the right. All right, so you just have to remember in that case, when you go to the table and you look up your test statistic z-score, it will give you the area to the left. And you just have to do 1 minus that area to the left to get the area to the right. Now, in the case where you have a two-tailed test, the p-value is equal to twice the area beyond the test statistic. So, if, say, your test statistic happened to be negative, so to the left of center, then you would just go to the table, you would look up the area to the left, all right? But then you have to take 2 times that area, because you also have to account for the symmetric area in the other tail. And vice versa. If your test statistic were positive, and if you look up the area, and then you do 1 minus the area to the left to find the area to the right, and then you have to do 2 times that. Okay, it's just basically because of the definition of the p-value, the probability of getting that sample or one more extreme. And with the two-tailed test, we don't know if it's going to be to the left or the right. So we have to account for the area in both tails beyond that test statistic. All right. Okay, I'm going to erase and move to the next page. All right, and then finally, I already mentioned this, but our decision criteria for the hypothesis using this p-value method, you are going to reject your null hypothesis if your p-value, I'm just going to abbreviate here, if your p-value is less than alpha, where alpha is your significance level. You're going to fail to reject if your p-value is greater than or equal to alpha. Okay? And again, the rationale. The p-value, it's just a probability. The probability of getting that sample data, assuming that the hypothesized value is true. Okay. Here's a probability of 0, a probability of 1. If you find that the probability is very small, okay, then the hypothesized value is probably not true. All right, so that is why we would reject. So again, your hypothesized value, whatever it is right here in the middle. If your test statistic, let's just say you're doing a right-tailed test, if your test statistic is way out here, and therefore that means that you just have a teeny tiny bit of area beyond that. Okay, so in this case, your p-value would be very small. It would be close to 0, meaning that, well, it's unlikely that this value is actually true, because your sample data, which is out here, is saying, well, I'm really far away from the hypothesized value. I'm so far away that the probability of getting me or anything higher is very small. It's very unlikely that that would happen if this is actually true. All right. So here's a summary of the p-value methodology, basically just the parts that are different from the classical approach. Steps 1 and 2 are exactly the same as the classical approach that we already went over. Step 3, the first part, actually calculating the test statistic, that is also exactly the same as the classical method. This portion is different. Okay, you need to use the standard normal table to determine your p-value. And again, that is based on what kind of a test you have and what your test statistic z sub 0 was. All right. Step 4 is how do you make your decision? If your p-value is less than alpha, then you reject. Remember, if the p-value is low, the null must go. And then step 5, which is just writing your conclusion statement, exactly the same as the classical approach. All right, I'm going to erase and go on to the next page. Okay, so let's go back to exactly the same problem that we were looking at before. If you recall, we already did this problem and we analyzed it using the classical method. Now we want to go back and analyze it using the p-value method. So we've already read through the problem. We've identified, all of the pertinent information from the problem. We already stated our null and alternative hypotheses. So again, we already know that the null hypothesis is that the proportion is equal to 0.33 because that's the value that it formerly was according to the 2011 information. The proposed alternative hypothesis is that, well, maybe it is no longer equal to that value. Maybe it's something different. All right, so everything's exactly the same there in step 1. Step 2, we already know that alpha is 0.05. That was given. Step 3, remember we already calculated this on whatever page it was a few pages ago when we did this problem before. And we already calculated that our test statistic based on the sample data was 2.04. Okay. All right, so here's where we're going to start the redo using the p-value method instead of the classical method. All right, so our step 3 now is determine the p-value. All right, so we already have calculated our test statistic. It is 2.04. All right, so in other words, this number is 2.04. All right. And then, you could think of it this way. Its symmetric partner is negative 2.04. And because we know this is a two-tailed test, and again, we know that because of this symbol in the alternative hypothesis, it's a not equals, which means that it is a two-tailed test. So because of that, we have to calculate both of these areas. In other words, the area beyond the test statistic times 2. Okay? So really, since our test statistic was positive 2.04, we want to find this area and multiply it by 2. All right? So, there's a couple of ways we could do that. We could go to the table and we could look up 2.04, find the area to the left, and do 1 minus that to find the area to the right. Or if we really want to, be a little more clever about this, we could just say, well, okay, let's just go look up negative 2.04 and find the area to the left of that. Because this area here is the same as this area here. All right? So if you go to the table and just look up negative 2.04, you should find that the area to the left of that is 0.0207. All right? So that is this area. But remember, we have to multiply that by 2. So in other words, our p-value is actually going to be 2 times that, 0.0207. All right, so if you do 2 times that, then you should get the p-value is equal to 0.0414. Okay. And then step 4, compare the p-value to the significance level. If p is less than alpha, reject the null. So the question we are asking is the p-value, which is 0.0414, is that less than the significance level, which is 0.05? Okay. Well, yes, 0.04 something is less than 0.05. Okay. So then we reject the null hypothesis. And of course, that's exactly the same conclusion that we had previously. All right, I'm going to pause there and go on. So I'm going to erase everything and scooch. All right, now for this exact same problem that we just finished, let's suppose we were doing the exact same analysis, except we wanted to use a 0.01 significance level. So in other words, alpha is now equal to 0.01 instead of 0.05. To test the claim that the current percentage of adults who have never consumed alcohol is different from 33%. Would that change the conclusion if we simply changed the significance level? Well, again, what we just did was we compared the p-value to the significance level. If p, and remember, we just calculated p, it was 0.0414. So now what we would say is 0.0414, is that less than 0.01? Okay, well, 0.04 something is not less than 0.01. No, it is not less than that. So does the conclusion change? Yes. Okay, because now we would fail to reject the null hypothesis. Because now we're saying, well, that sample data, I want to be even more sure that it actually did change. And now I'm saying, well, that sample data, no, it was not extreme enough to cause me to reject my null hypothesis. All right. And I think it's a little bit more difficult to think about with the p-value method maybe, but maybe it's easier to use the classical approach to visualize the problem, okay? Because we had previously done this with the classical approach, and it was a two-tailed test, and so we had found that our critical values were negative 1.96 and positive 1.96. Okay, so that was at a significance of 0.05, which means we have 0.95 in the middle. So these numbers are familiar. negative 1.96, positive 1.96. And when we compared our test statistic, it was 2.04, which was just a scooch past the critical value, so we rejected it. Okay? But if we had a significance of 0.01, which means there's only 0.01 total in the tails divided by 2, or 0.005 in each tail, that moves the critical values further out. And in fact, they're at plus or minus 2.575. Okay. So these would be the critical values corresponding to an alpha of 0.01. So positive 2.575, negative 2.575. So now you can see that our test statistic is now inside the critical area. It's in the do not reject. Now we're saying, okay, it's close enough to the middle. We're not going to reject the null hypothesis. Okay. So kind of the bottom line is, with the significance of 0.01, the critical values have been moved farther or further, I'm not sure which one is correct, more away from the center. Okay? So in other words, your sample data has to be even more extreme for the null hypothesis to be rejected. Okay? It's kind of like, I want to be even more sure. And it's kind of the same concept that we went through in chapter 9 with the confidence intervals. With a higher confidence level, you know, like 99% versus 95%, your intervals would become wider to include more possible values. Okay? Now, it's kind of the opposite with the smaller significance, 0.01 instead of 0.05. The interval of sample values that may have come from a population that's centered in the middle also becomes wider. All right. Okay, I'm going to erase and move on to one more page. So just a quick note that you can use StatDisk for this, and you might want to use this just as a tool on checking your assignment 10. So you go to Analysis, Hypothesis Testing, Proportion 1 Sample. Now the most important part about this is right here at the start. Okay, the drop-down menu here is where you enter the correct form of your alternative hypothesis. Okay, so there's an option here in the drop-down menu for not equals, or for less than, or for greater than. So whatever your H1 is, you have to make sure that you pick the correct option here. Then you just put in your alpha, okay, your significance level. You put in your claimed proportion, all right, what you think it is. This is your P0 that corresponds to whatever number you have in your null hypothesis. Put in your sample size N, your number of successes, hit evaluate. It will show you, it will calculate the sample proportion P hat for you. It will calculate your test statistic, that is your Z0. It will find the critical Z values for you, or maybe only one. So that's corresponding to the classical method. It will calculate the p-value for you based on the p-value method. All right. And then it doesn't actually tell you the conclusion. You have to use this information then and make the correct conclusion. And then everything down here is exactly the same. So this was the problem the first way we did it with alpha of 0.05. We calculated this test statistic. We looked up these critical values. We calculated this p-value. Okay. The only thing different here was when we changed to 0.01, our critical values changed. Okay. All right, I'm going to erase. And actually, I'm just going to stop there. So if you have come to the end of this, and I hope you have, you now have all the information that you need to do that assignment, that Chapter 10 assignment. And that was kind of my goal. So please start working on that. Start sending me stuff so I can look at it for you. I am going to, go over this material again in class on Monday. My goal wasn't to substitute for that, but to allow people to get a jump start, basically. So you can either come to class on Monday at our normal time and get kind of a rewind of this whole lecture, or if you prefer, come a little bit late. I'm going to say about an hour late. So if you want to show up an hour late, then what I'm going to do beyond that is we will then, work through another problem, and we will do one more sampling experiment, the M&Ms. All right. So however you choose to do that is fine, but I do expect to see you on Monday. All right. Bye.